Okay. So. All right. So we continue on with chapter 7, which is on kinetic energy and work. Now, we did start a little bit before the midterm last Monday, but I will go over it again just to be safe. So, as we said, energy is a scalar quantity, so it's just a number and a unit, no direction, which is assigned to an object or a system of objects. Okay, so far so good. We said there are many different types of it. So we can change it from one type to another. And we said that what we're going to do is we're going to be taking a look at multiple types and then forming a general conclusion on the matter. So kinetic energy, we said, is the energy of motion. Whenever something is moving, it has energy. For an object with a velocity that is well below the speed of light, so very, very low percentages, okay, if any, the translational kinetic energy key of an object is defined as half mv squared. And the unit of the kinetic energy is joule. Now, there's a lot of information in this slide, even if it doesn't show it. So we define kinetic energy as the energy of motion, which means that if anything is moving, it has an energy. We restrict our definition to well below the speed of light, because when you get near to the speed of light, weird things happen. Okay. And we say that the translational kinetic energy is half mv squared. And translational has 2-3 lines under it, because that also means when we specify translational kinetic energy, it also means that there are other types of kinetic energy. So, for example, rotational kinetic energy, which we will study about in chapter 9-10. Okay. Joule is the unit of kinetic energy, but can anyone think of some other type of unit for for energy in general, not even kinetic energy, just energy? Can anyone think of a different unit?
Electron volt.
Okay, electron volt is an excellent unit of energy. It's a tiny unit of energy, which makes it ideal for using it in particle physics, quantum physics. Okay. Any other units?
Yes, what about the Newton? Meter per second.
Meters per second is velocity, so it cannot be for energy. Newton is for force, so it cannot be for. So it also cannot be for energy.
Calorie.
Watt is for power, which is energy per time, but that is a good start. That is a very good start.
What?
Someone said calorie. Calorie is indeed also a unit of energy. And if you are as fat as I am, then it is a very important unit of energy, because you need to make sure what you eat is, not going to make you even fatter than you already are. So we have 3 units now. We have the joule, we have the calorie, and we have the electron volt. Okay. Good. These are really good. So, but the SI unit is, of course, the joule. And we'll stick to the joule for most of this course. Now, if we know that the kinetic energy is equal to half mv squared, that means that different objects with different combinations of mass and velocity can have the same kinetic energy. And you can think of it in this way. Say you have a wall and a car hits that wall. Now, if a trailer, big truck, hits that wall, what's going to happen? It's going to pretty much, get destroyed immediately. Even if it's at low speed. دفرة بسيطة والجدار طاح. But if I want to take the same wall down using a Corolla, how fast does that Corolla need to be to make it fall down? Quite fast. Because if you want the same amount of energy from a Corolla and a big truck, you need to go at a much higher velocity in the Corolla to compensate for the low mass of the car. Now, you remember the scalar product, A dot B equals AB cosine theta. And it takes two vectors, A and B, and gives you a scalar, just a number, no directions. Why is this important? How are we going to use it? Let's talk about something first before we go further into this slide. How many times did this happen to you? And I know this happens to everyone, so, I'm pretty sure it happens to everyone. Your mom asks you to do something. Okay? روح أو روحي يا فلانة وفلانة, do this thing. Now you spend so much energy and you work وتتعب وتسوي, وبعدين mom comes, they go, nope, لو ما سويت كان أحسن, ما منك فايدة, ما سويت الشغلة عدل. This happens? I know it happens. Don't be shy. Okay. Turns out, moms are not really happy with the work being done. They want it done in a very specific way. Okay? It's not enough that you do the job. It needs to be done exactly the way that moms want it to be done, or كأنك يا أبو زيد ما غزيت. Yes? Turns out, physics is very similar to moms, or maybe our moms just took it from physics. I don't know. Okay? Because in physics, the concept of work in physics has a very specific meaning. And unless you do it in that specific way, it doesn't count. Okay? So the definition of work in physics is F dot D. So FD cosine theta. Which means if we look, now if I have a force F pulling this green block from point A to point B, F cosine theta is parallel, so the theta is 0, the angle is 0. Cosine 0 is 1, so you get the work component along the x-axis. What about F sine theta? How much work does it do, according to the definition we have on the slide?
0.
0, nothing. The angle is 90, right? So if I have something here at point A, and I want to go to point B, what path should I take to make my work really count? What's the best way to do it?
Angle
Take
0.
the F to
Straight line.
parallel to
Yeah, all of them are good. So I need to make the force parallel and go in a straight line to make my work really, really count, right? Because D is the displacement, yeah, and this is a very important point. D is the displacement and not the distance. So if I go straight line from A to B, or I take this path, the amount of work done according to physics is exactly the same amount of work. Okay, so I might as well just take the shortest path because that's what I'm going to get credit for. Okay.
Doctor,
Aywa.
can you repeat this point?
So F dot D, what is D in this equation? D in this equation is not distance, it's displacement, right? Final position minus initial position. Remember when we were looking at velocity and at speed? And we could find that something could have a very high speed but a very low velocity because only the displacement mattered, not the speed, not the distance. Do you remember that?
Yeah.
Yeah, it's the same here. Since D is displacement, okay, you only care about the straight distance, the displacement between points A and B. So if we take that very, very long path, the amount of work I have done according to physics is exactly the same as if I have gone from A to B. Okay, it's like when, mama says do this, and you decide to do that and a bunch of other things. It doesn't matter what other things you do. Okay, it's only what she asked you to do that matters. Now, these equations are only for constant forces. Okay, if my force changes while I am doing the thing, then I need to integrate the force with tiny, tiny paths. So I need to do F dot D for tiny, tiny D's, F dot D, 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 like this, and add them all up, which is integration, F dot dr. And we'll do that later on. Okay, here's a boy or a girl on the left who is lifting 50 kilograms of weight on top of their head and keeping it up there. What's the work that person is doing while staying like this?
nothing, 0 work.
Zero work, right? Because the thing is not moving, so displacement is 0. What about that poor guy trying to push a car?
If it moves, then
How much work?
there is work.
Yeah. If it moves, then there is work being done. But if that car is not moving, and let's be honest, that person pushing that car is not moving, okay, then there is no work being done. Okay, which sucks. 0 displacement equals 0 work. It doesn't matter how much effort you put in. It's like that time, my mom asked me to clean up the hall because we had guests coming over, and I cleaned up the entire hall, but I forgot a piece of tissue, which meant, according to my mom, that I did not clean the place and I did not do my job. It doesn't matter how much cleaning I did of that room Because if that piece of tissue was on that table, that meant I did not do my job well. Okay? And according to physics, it doesn't matter how much work you do, how much force you exert, how much pushing you do. If that thing does not move, you have not done your work. Your work done is still 0. I have a question. What if I have 3 people pushing a really heavy object to move it? What is my total work done?
The sum.
The sum of works. So
No, the sum of force times displacement.
yep. So I find the total force, F1, F2, F3, and then I multiply it by the displacement. Or if I know how much work they do already from some other source, then it's just W1 plus W2 plus W3, right? Now some of you might ask, okay, ليش مصدعين راسنا نحن? What's the point of all of this? We have spent chapter 5 and 6 and chapter 3 looking at vectors and looking at forces, and we can add forces and subtract forces, and we can just find whatever we want using forces. Why do we bother looking at work? Okay, what's the point? Now there's more than one point, but I will tell you one point that is not mentioned in your book. Okay, but which is quite important. Say you are a computer and you want to do F1 plus F2. How do you do it? You need to look at the XYZ component of this, plus XYZ component of this, and then you need to add. If you have angles or if you have magnitudes, then you know you have magnitude of this, and you add, and you take square root, etc. So what is the minimum number of steps I need for F1 plus F2 computationally? How many steps do I need to do? نايمين اليوم. So here I need at least 4 steps. 1 for adding x plus x, 1 adding for y plus y, and 1 for adding z plus z, 1 for adding the magnitudes. Minimum. So it means degrees of freedom equals 4. While if I just do W1 plus W2, how many steps do I need here?
1.
Just 1 step. Which computationally means it is much, much faster. Now, a normal computer, okay, will have the time taken for a calculation is equal to the power of degrees of freedom. So for W1 plus W2, it will be done in time 2. While for the other one, it will be done at 2 to the 4, 16. So 8 times as much time you need. Okay, so computationally, for example, this is a very useful way to look at things. Never mind that in physics, there are sometimes you don't know the force. We need to look at the powers or at the energies and all of these other things. Let's look at the dependence of angles, since work is Fs or Fb cosine theta. I'll use Fs here, Fs cosine theta. When my angle is anywhere between 0 and 90 degrees, my work is Fs cosine theta. What about when my force is parallel? Theta is equal to 0. Cosine 0 is equal to 1, so I get my maximum force, which is Fs. What about when theta is equal to 90 degrees? So my direction is, my block is moving to the right, but my forces are up or down. What amount of work is that force doing?
0.
0. Cosine 90 is 0, so that thing is not doing any work. So let's take a look at this guy. He works at Barid Oman or Asyad Express or Mandub or UPS or DHL, and he has a heavy box and he's running. What is the work done by gravity in this case? 0. Nothing.
0.
Because it's at 90 degrees. Yeah. So according to physics, when you hold a box at rest or you move with a constant velocity, okay, then your work done is 0. Which makes no sense to me because, when I hold a box beside Mama when she's tidying up the kitchen, that box becomes really heavy even if I'm not moving it. Just holding it in my hand becomes heavier and heavier and heavier. But according to physics, I'm not doing any work. I'm just chilling. Okay, I just need Netflix and then I can Netflix and chill. What about when theta is equal to 180 degrees? When theta is equal to 180 degrees, I have cosine 180. So say, for example, I am moving something to the right, and then friction is to the left. What is the amount of work that friction does?
Negative.
Minus.
So it's going to be minus, right? And many times the work done by friction forces are negative. They take energy away from the system. Now knowing, actually I'll come back to that in a bit. Never mind. So let's say, actually, let's go back. Knowing that kinetic energy is equal to half mv squared, and that, well, kinetic energy and work is also energy, okay, what is going to happen to the energy content of a system when friction does negative work on it?
Decrease.
It will decrease, right? So if my K decreases, what else decreases?
The speed.
My V decreases, right? Now if I'm close to the speed of light and funky things are happening, E equals mc squared, hadith alpha thaniya. But here, my mass is constant and my velocity decreases. So if I do negative work, I get less energy and my velocity decreases, which means that if I do positive work, my energy content increases and my velocity increases. Now, a block is on a rough surface. Someone pulls the block with a force F with some angle theta. The block then accelerates to the left. What is the sign of the net work done on the block? Positive, negative, net work is 0, or I have no idea. Type it into the chat box. I'll give you a minute to think about it, and then you can just type it into the chat box.
دكتور
ايوه
اقول لك لو تخلي الاي بي كيو كوتشن لو تخلين مثل الكوز مثل اول الايام عشان لما يصير تقييم درجات هنا انت ما تعرف احنا جاوبنا ما جاوبنا.
We will start back الحين من المحاضرة الجاية ان شاء الله. We will return to the PIQ system. اللي هو مال الموديل.
ايوه لان احنا نستعمل بعض الطلاب ايباد او تلفون فما يظهر معهم.
ايوه لا راح نرجع للموديل سيستم. بسبب اننا نحن توقفنا نستخدم الموديل في الاسبوعين الاخيرين هو انه كانت صايره اشكاليه في الموديل من السي اي تي، وكان كل ما احاول I create a question it takes ages لانه كل شويه يقول لي security action failed ف I could not create them. بس الحين المفروض نظريا انهم يوم الخميس الماضي خلصوا maintenance و it works. So hopefully اليوم راح اجلس عليه وراح احاول اني ارجعه كيف ما كان، يعني ابدا اسوي البي اي كيوز مره ثانيه من اول جديد.
ان شاء الله. احسنت ما تقصر.
It's also better for you حال الريفيجن و it's also more exciting عن الchat box. Okay, so pretty much everyone chose A, and A is indeed the correct answer. So I have force F coming this way, which means that I have F cosine theta, F sine theta, mg, normal force, friction. N and mg are perpendicular. F sine theta is perpendicular. Now I have F cosine theta doing positive work and friction doing negative work. Now, since the block is accelerating to the left, that means its velocity is increasing. And if its velocity is increasing, that means its energy is increasing, which means the work done is positive. We're giving it more energy. Now, here's the question. What if it said the block moves at a constant speed or constant velocity? What would be the sign of the network done on the block?
Zero.
Good. It's going to be 0 because if there is no acceleration, i.e. there is no change in velocity, it means that my work is constant. Sorry, my energy is constant, which means that whatever positive energy comes from my force is going to the negative side in friction, and the net is 0. So my energy content does not change, so my velocity does not change. Now let's do an example with some numbers. A 4 kilogram box is pushed by a force of 50 newtons, making an angle of 37 degrees with the horizontal. The coefficient of friction between the box and the surface is 0.4. If we displace the box by 2 meters, what is the work done by all the forces acting on the box? So we start by drawing a free body diagram. This is my box. Can you tell me what forces are on it?
Gravitational force, natural force,
Okay, bad.
friction force.
Friction force.
Force applied.
And force.
Bad.
Yeah.
That's it? Okay. So to start with, we can tell immediately that the normal force mg and f sine theta are at 90 degrees, which means they do no work. That leaves us with friction and f cosine theta. Now f cosine theta, the work done by friction, sorry, the work done by the force is 50 newtons times cosine 37 times the distance, which is 2 meters. That's 80 joules. Gravity and normal force are 0 immediately, and that done by friction will be FKS cosine 180 degrees. It's in the opposite direction. I substitute for FK with mu Kn, and I end up with minus 56 joules. So I'm inputting 80 joules. I am taking off, the friction is taking off 56 joules. And the difference between them is what causes the acceleration. Now we have talked a lot about, when work is more, energy is more, and velocity is different, but we have never formalized it mathematically. So let's do that. Work done by the force is F dot D, or in this diagram it will be Fs. We know from Newton's second law that F equals ma. What is A? Now, for moving something, we have v squared equals u squared plus 2as, which means A equals v squared minus u squared divided by 2s. So we can substitute. W equals Fs, F equals ma, A equals that thing. And when we substitute the whole thing, we end up with work net is equal to half mv final square minus half mv initial square. So final kinetic energy minus initial kinetic energy, which we call delta K. So the work done is equal to the change in kinetic energy, and we call this the work energy theorem, or otherwise known as WET, WET. So to summarize, the work energy theorem states that the net work done on an object is equal to the change in its kinetic energy. If the net work done is positive, the kinetic energy increases, velocity increases. If the net work is negative, then the kinetic energy decreases and velocity decreases. So far, so good?
Yes.
Let's do a numerical example from your book. Sample problem 7.02. See, you have two people trying to move a safe. One is pushing, the other one is pulling. Person pushing is putting 12 newtons at 30 degrees. Person pulling is putting 10 newtons at 40 degrees. And they need to move it for about 8.5 meters. What can we do with that information? Well, first thing first, free body diagram. Now, since there is no friction mentioned, I'll leave friction out of it. A, what is the net work done on the safe by forces F1 and F2? Displacement is 8.5 meters. Theta is equal to 30 and 40 degrees. So let's do them on their own. Work done by force 1, FD cosine theta, 12, 8.5 cosine 30. That's 88.33 joules. And by W2, it's going to be 65.11 joules. So the total is 153 joules. During the displacement, what is the work done by the gravitational force and by the normal force? since they're both at 90 degrees, we can simply write 0 without doing any other work. 90 degrees, 0. The safe is initially stationary. What is its speed, Vf, at the end of the 8.5 meters displacement? Now, there's more than one way to do it. We can do it our normal way using our equations, but there's an easy way to do it. Net work is change in kinetic energies. Now, since we started at 0, we want to know what is the final energy, and we know what is the total work done. So we simply rearrange. We know our total work is equal to 153 joules. So 153 joules, 225 kilograms, and it immediately tells us 1.17 meters per second. Without going through any really complicated calculations, knowing the times, knowing the velocities and acceleration distances, etc. Very, very easy. Let's try this question. Determine the amount of work done in firing a 2-kilogram projectile to a speed of 50 meters per second. Neglect any effects due to air resistance. So 2 kilograms, you're firing a projectile, so initial velocity is 0 and final velocity is 50 meters per second. We don't know what the launch angle is. Can we know the amount of work done? I'll give you a couple of minutes, try it out. Okay, let's take a look at the answers. Okay, pretty much everyone got the right answer. C. Excellent. And as you can see, this is much simpler than simply doing a... This is much simpler than just, doing a projectile motion calculation. We don't need all the details. We know the initial speed, we know the final speed, that's all we need. The path it takes doesn't really matter. Okay, so that was the kinetic energy. Let's take a look at a different type of energy, the gravitational force or gravitational energy. Say we have a rock and we want to move that rock up. What is the work done by gravity force while we are moving it up? See, I'm not asking for the net force. I'm only asking for the force done by the gravity itself. It would be negative, right? Because F dot D, yeah, F is mg, D is this distance, cosine theta, and my theta is 180 degrees. Okay? The force is down, the movement is up. So I end up with minus mgd. Okay. Now, what about when I drop it down? When I drop it down, okay, my force and my displacement are in the same direction. So again, mgd cosine theta, only my theta is now 0, so positive mgd. So technically speaking, if I take something, I take it up and I drop it back down, my net work is what? Simply zero. Okay. Now all of this might seem like it's useless. So let's try to find out why is it useful. Now, while I am moving the rock, I need a force to take it up, صح؟ أنا قلت إنه الجرافيتي الورك ماله نيجاتيف وتحت والفورس تحت. لكن I need to do work. I need to get a force to move it up. So if I start at velocity not equals to 0, move the rock up and then stop it. So initial velocity 0, final velocity 0. And we said that the kinetic energy is equal to final kinetic energy minus initial kinetic energy. What is the final kinetic energy?
0.
0. Initial kinetic energy?
0.
انزين. طيب إذا ال change in kinetic energy is 0. معناته أنه work done is equal to exactly minus the work done by gravity. إذا الجرافيتي جالس يسوي work minus 10، أنا لازم أسوي زائد 10 عشان أوصله فوق. وهكذا. طيب. تو أنا عندي سؤال. What's the point of all of this? جالس نضيف MGD energy is 0. إيش الهدف من الخبصة هذه كلها؟
Here we don't have change in kinetic energy, but there is change in potential energy.
Ah, good. This is a very good observation. We have what is called a potential energy. So when we are lifting the rock to a different height, it's like we are storing energy in it that we can use later on. But we'll come back to this in a second. Okay. Note that the works do not need to be equal. They are only equal in this case if the initial and final kinetic energies are equal. Okay, so if initially 0, finally 0, the works are equal. Now, if the works are not equal, that means we have a change in velocity. Now, let's do an example. Hello, can you hear me?
Yes.
Okay,
Yes,
did I
Mr.
disconnect for a second? اوكي، ايش اخر شيء سمعتوني اقول؟ احس كاني انقطع علي شويه الخط.
قطع شوية يا دكتور، عندك صوت.
أول ما انتقلت للبي آي كيو بالأكثرية.
انزين. Okay. If we have an elevator that is supported by a cable and it goes down at some constant speed, okay, the only forces acting on the lift are tension من الكيبل or gravity downwards. Which one is true? The work done by T is 0 joules. The net work done by Fg and T is 0. The work done by Fg is 0. The magnitude of the work done is more than magnitude done by the other. Now I have already ticked on the net work done by Fg and T is equal to 0. But my question is why? Why is the net work done by Fg and tension is 0? Can anyone tell me? I've doodled some clues on the page.
One of them is positive and the other is negative, so they cancel each other.
Okay, but how do we know that? What is our proof?
Because the A equals 0 and net force equals 0.
The elevator is going down.
Okay, how do we know that A equals 0? أنا كاتب A equals 0 بس كيف نعرف؟
Doctor, like the air drag, if the velocity is constant, so the Fg and T are equal.
Very good. The key term here is constant speed. Because it's constant speed, it means no acceleration. Because no acceleration, it means no force. Because no force, okay, that means my work done is equal to 0. But obviously tension and gravity do work. So that means my net work is 0, and that means that T equals minus Fg. Work done by one is minus the work done by the other. Okay. Now this is an interesting thing for those of you who are interested in technology. Now we have satellites that have circular orbits. Yeah, Arabsat, Nilesat, telecommunications. At a certain orbit R, that satellite is going round and round and round. What is the work done by gravity on this satellite? The satellite has some mass m and some speed v. Now, most commonly, when we think about this, we say the work done by gravity is 0. لأنه there is nothing that pulls it out there, and the thing is not falling inside to Earth, which means that 0 work is being done on it. صح? What if I tell you that there is actually work being done on those all the time, and it is equal to mv squared over 2? I can imagine.
Because it is in circular motion?
Because it is in circular motion,
Change
velocity
direction.
changes all the time, which means there is acceleration. حتى إذا the speed is the same, there is acceleration لأنه direction is changing. Okay. But then if there's work being done on it and there's acceleration, why isn't it falling down? Because its direction of movement is always perpendicular to the direction of gravity. The direction of movement is always perpendicular to the direction of gravity. Always, always, always.
Doctor, what if it stopped?
If the satellite stops for any reason,
Yes.
if the satellite stops for any reason, it's going to fall down back to Earth. Because then the network is not going to be equal to 0. It will no longer have the kinetic energy of a half mv squared going round and round and round. Yeah. So what happens is, where's my whiteboard? So what happens is, this thing is going in a circle, صح? It's going at a velocity, so it has energy here, half mv squared, and gravity is pulling it at half mv squared. So the speed is equal to, change in speed is 0, but the velocity, it keeps changing direction. Now what happens if this velocity is decreased? The amount of gravitational pull on it does not decrease. So now suddenly you have a net work and net force, which means it's going to start falling down. But interestingly, it does not fall down like this. Do you know how our satellites decommission from orbit? Say, for example, the old Arabsat satellite has been out there for now 30, 40 years. Well, it's no longer working. They want to decommission it. How will they decommission it? Do you know? What do they do? Any idea?
I think they designed it to fall in the water.
Yes, but how do they make it fall? Yes, Mariam has said it correctly. يقلل السرعة. All they have to do is fire a tiny, so this is your this is your satellite, and all they have to do is they have a tiny engine here, booster engine. Okay, tiny one with a small can of gas. تعرفوا لما نروح نشوي بالعادة أو نروح مثلا البر نودي معانا كذاك كأنها غرشة صغيرة مال غاز. So it has something that size, and what happens is there's no friction out there, you don't need much energy, and they start firing these, all 4 of them. Okay, and this reduces the speed. As soon as speed is reduced, you have a problem. Your balance between gravitational and centripetal force and this work being done at 90 degrees all starts getting screwed up, and this thing starts going. Say they do this here, it starts going like this, and then they slow it down again, and it goes like this, and then they slow it down again, and it goes like this إلى أن تطيح في البحر. It will just keep going in circles and smaller إلى أن تطيح في البحر. Yeah. So although there is a force, okay, the displacement in its direction is 0, so F dot D is equal to 0. See, this is what happens. You have the satellite, and your force is down this way, and your displacement is this way, and you have 90 degrees between them. So you have mg dot D, and you have cosine 90, so your work done is 0. So it can keep continuing going in a circle. You mean why not keep it in space, Amjad?
No, just throw it in space. Increase the velocity, and he will go away from Earth. Why they bring it back to Earth?
So you mean just throw it outside in space, chuck it outside, صح?
Yes.
Gravity is a very, very, very strong force, believe it or not. Okay? If you have ever fell and broke a bone, you know how bad gravity is. Now, here's the thing, okay? Because gravity is such a strong force, you have a problem. Getting out of gravity, and we will actually study this a little bit in chapter 13, but not in a lot of detail. Getting out of the well of gravity of Earth takes shitloads of energy. Okay, so what happens is, if we go back to our whiteboard, say this is the original orbit, this is Earth, this is the original orbit of the satellite, صح? Now, if we increase, now of course we have one problem which Mariam has mentioned, تلوث الفضاء. Okay, but I'll come back to that in a second. Now, if I increase the speed a little bit, okay, it's going, say I increase the speed at this point, it's going to go like this, صح? Now, as soon as I switch the engine off, what's going to happen?
Continue in circular motion.
بيرجع circular motion but with a bigger orbit, صح؟ انزين ابغى ابعده بعد اكثر، لازم بعد اسوي extra energy. كل ما اريد ابعده اكثر واكثر it becomes more and more difficult. Okay, actually we have an excellent example which happened 2 weeks ago, so I can use it immediately. Okay, here's the thing. مؤخرا الامارات ارسلت مسبار للفضاء، صح؟ قبل اسبوعين راحوا للمريخ. كلكم سمعتوا بهذا الشيء؟
ايوه.
اوكي. الحين اذا تتابع الاخبار وتتابع علوم الفضاء، انزين، بتشوف انه سالفه كبيره. خليك من هذا، خليك من المريخ. اقرب جرم سماوي الينا هو القمر، قمر الارض، صحيح؟ انزين. How much energy do you need to go from Earth to the moon? You need to do a lot of work, because Earth's potential energy, the mg, is very, very strong. The gravitational pull, the force, is quite strong. So to get totally out of it, okay, you need to put in a lot of work, a lot of energy, which means you need to burn a lot of fuel, and it's just too expensive. Yeah. Remember, انت ما عندك محطة بترول في الفضاء عشان تودي لها بترول الساتلايت بعدين. اوكي، whatever is there، يعني هذا الاسطوانة الغاز هذه اللي يستخدموها to slow down the speed، هذه ما يودوها بعدين. It launches with the satellite. قبل 30 سنة يوم they launched it في الفضاء it was with it داخلها. الحين إذا أنا أريد أوديها بعيد، أوديها للقمر، زين؟ طيب ما ننسى أنه نحن كل يوم we are launching more satellites. Eventually you will run out of space ويصير عندك تلوث في الفضاء، يصير عندك زحمة، بتضطر تودي معاك مخمة كبيرة وتبدأ تنظف في الفضاء، which is very, very difficult and very, very expensive. Okay, but aside from that الحين إذا أنا أريد أوديها بعيد، إنزين، نقول هذه هي الأرض، هذه هي القمر، هذا هو القمر، إنزين، أقرب كوكب لنا هو المريخ. So theoretically إذا ما نريد نسوي تلويث الفضاء، إنزين، نحن نريد نشيل الساتلايت من هنا ونعقه هنا بعد القمر. طز اللي يصير بعد القمر طز، ما فارقة معانا، زي ما تيجي. إذا في كائنات فضائية خلي تدعم فيهم، ما فارقة معانا. Good enough؟ إنزين. let's see your general info. من يعرف هنا كم المسافة بين الأرض والقمر؟ يعطيني تقريب.
3 مليون كيلومتر أتوقع.
Okay. Let me teach you something. في المسافة ما بين الأرض والقمر I can fit in. من يتذكر الكواكب؟ الزهرة، بعدين عطارد،
أو العطارد بعدين
أو العطارد بعدين الزهرة. عطارد، الزهرة، الأرض، المريخ، المشتري، زحل، نبتون، أورانوس، بلوتو. طبعا بلوتو الحين طلعوه بس أنا ببقي بلوتو هنا لسبب. Do you know that في المسافة ما بين الأرض والقمر I can fit all of these in here بدون مشكلة؟ That's a very big large space. So giving something enough energy to get out of it is a very, very huge very, very huge cost and a very huge problem. This is why sending even a tiny rover to Mars is considered a big thing. Okay, it's considered a big thing because it's really, really difficult. And I'll actually tell you one more thing. Do you know that when we send مثلا Galileo أو مثلا Hubble telescope أو هذول الروفرز إلى Mars, we don't use fuel all the time to get to them? Because remember, this is your rocket. Okay, this is where the people are, and this is mostly fuel. صح? Now the more you want to go out, the more fuel you need to add. صح? But the more fuel you add, the more mass you have, which means you need to add even more fuel, which means you are adding even more mass, and so on and so forth. And it quickly becomes very, very expensive. So what happens is usually they have just enough amount of fuel to get them out, وبعدين they use what we call a gravitational slingshot. تعرفوا المقلاع اللي نحط فيه الحجرة وندوره فوق راسنا وبعدين يوم نفلته الحجرة تطير؟ We do the exact same thing, but with rockets. So what we do is, believe it or not, okay, we do it around Earth. So we send a spacecraft outside, وبعدين we make it come all the way here and we stop the engine. نخلي جاذبية القمر هي اللي تسحب المركبة. من توصل قريب القمر we make it start going around the moon to pick up energy. وبعدين نفلتها مرة ثانية. it goes بعدين all the way like this كأننا فلتنا حجرة بس هالمرة فلتنا صاروخ من جاذبية all the way to Mars. وبعدين if you want to go to further planets, they do the same thing here. They do like a slingshot, and it goes to some other planet. It's very fun if you think of it, you know. It's like rocket Tarzan. But instead of, you know, going from one tree to another, you're going from one planet to another. Which is still fun in my opinion. Okay, so it's, long story short, it's just easier and cheaper to make it come back to Earth. Okay. This is a long, long chapter. Okay, Let's end this lecture with a sample problem. Let's end this lecture with a sample problem. Sample problem 7.04. An object is pulled along a ramp, but the object starts and ends at rest. Okay. So a rope pulls a 200 kilogram sleigh up a slope at incline angle theta equals 30 degrees. So sleigh mizlaj, same as a, Santa Claus, Baba Noel, through a distance d equals 20 meters. The sleigh and its contents have a total mass of 200 kilograms. The snowy slope is very, very slippery, so we take it to be almost frictionless. How much work is done by each force acting on the sleigh? So you have the sleigh, 200 kilograms at 30 degrees, it's going up 20 meters. So say, for example, I am pulling it here by a rope, which means somewhere here, I will need an engine. And I need to figure out how much work should this engine be doing. I'm designing the system. So we start at 0. ولما نوصل فوق نوقفها. We want it to be 0 as well. First thing first, free body diagram. And then a down mg. And then along the slope, tension of the rope. And then a perpendicular normal force. No friction. Yeah? So far, so good? Anything I have forgotten?
Good.
Okay. Let's first look at the work done by Fn. The direction of motion is along the slope, x-axis. Fn is along the y-axis. What is the work done by Fn?
0.
0. Simple. What about mg? What is the work done by mg? mg is not on the x-axis or on the y-axis, so we need to resolve its components into x and y. In the x direction, we have 90 degrees. In the x direction, we will have mg cosine theta. In the y direction, we will have mg sine theta. So we put mg d cosine the angle 120 degrees, which means we get a number which is negative. Which makes sense. I mean, if you're thinking about in terms of forces, yeah, we will have mg sine mg cosine theta here. We'll have mg sine theta here, صح? Down. So it means it's opposite to the direction of motion. So the work done is negative. Makes sense. Work done by tension. Work is equal to F dot D, tension dot D. What is tension? What is the force my tension here? Do I know what tension is? I don't. Okay, so how do I do this? Well, I can assume what is the minimum amount of work, minimum amount of force tension should have to be able to pull this sleigh back up. At minimum,
Less than W.
Yep, exactly. Minimum, it needs to be equal to mg sine theta. اللي هي in the opposite direction, صح? At the very least, it needs to be هذا زائد تتون to be able to pull it up. So, I will substitute mg sine theta for d. Okay. And I will end up with the work being 1.96 times 10 to the power 4. Okay. What is the work done by the rope's force? Now we have two methods to do this. Method 1 is what we did. We calculated. Method 2, since our initial kinetic energy is 0, our final kinetic energy is 0, total kinetic energy change is 0, we know that the sum of all the works is equal to 0. So work done by N, by the normal force, is 0. Work done by gravity is equal to 1.96, which automatically means work done by the tension in the rope is minus that. Any questions? You can stop here today. Do you have any questions?
About the midterm, Doctor?
No, about the lecture.
No.
No. Okay.